to interpreting and drawing amino acid titration curves. I know that you all have a lot on your plate and your time is precious, so I'm going to try to make some more concise videos in addition to the longer videos in which I give more details for those who want it. But hopefully, if you just need to review or something like this, these videos will be helpful. When you look at an amino acid titration curve, it can look a little intimidating. So first, let's just go and let's look at how we can interpret one of these, and then we'll look at how we can draw one of these. First off, this thing at the top, this is just some shorthand notation that I'm using to represent the ionized state of the N-terminus or of the C-terminus. And when we talk about ones with an third ionizable group with the R chain, I'll be drawing that above, and I'll introduce this notation a little later. But this is corresponding to the charge states at those different ionizable groups as you add OH minus equivalents. So basically, you're going to start with the fully protonated state, and then you're going to start adding OH minus equivalents, or at least pretending you're adding OH minus equivalents, and then thinking about what groups are going to deprotonate. So you need one OH minus equivalent in order to deprotonate a single group, and you need two to deprotonate a second group. In the case of an amino acid, you're always going to have at least two ionizable groups, the N-terminus and the C-terminus, and they're going to deprotonate in order of their acidity, so increasing pKa values. Your C-terminus is going to deprotonate first, followed by your N-terminus. It's going to take one OH minus equivalent to deprotonate that carboxyl group on your backbone, and then a second one to deprotonate that N-terminal amino group. What's going to happen is that when you're at those full OH minus equivalence points, you get an equivalence point, which basically means that you've depleted all of that acid. This is going to correspond to this to the steepest parts in the curve, because when you're at those points, then you don't have any of the conjugate acid to neutralize the base. So if you add more of the NaOH, well, now your pH is going to shoot up. So on the x-axis, we have our OH minus equivalents. You might also see this as like NaOH or KOH. But remember, when you dissolve those, they'll dissociate, giving you your hydroxide equivalents. And then on the y-axis, what we have is the pH. And so once we add more OH minus, we're going to increase our pH. If we're in one of those buffering zones, we're going to not get much of an increase in the pH, so we'll get this flash zone. But if we're near an equivalence point, we're going to have depleted our acid, and therefore we're going to get a steep rise in the pH. Now, when you have something like an amino acid that's either diprotic, or as we'll see with the ones with the ionizable side chains, they're going to be triprotic. They're going to have three ionizable groups. What happens here is that we're going to get multiple buffering regions. We're going to have multiple of those flat zones. We're going to have one around the pKa of each of the ionizable groups. We're going to be thinking in terms of one group at a time. So each of these groups is going to have its own pKa value corresponding to the point at which there's half of that group is protonated and half of it is deprotonated. In this case, our pK1, so for our carboxylic acid in the backbone, this is typically going to be somewhere around 2. And at that point, you're going to have half of it be in the protonated state and half of it going to be in the deprotonated state. As you deplete that protonated state, you're reaching your inflection point. You start shooting up in your pH. But then what's going to happen is that second group, that amino terminus, is going to basically start deprotonating. And that's going to give you a new conjugate acid corresponding to that N-terminus. Now you have acid again to neutralize the base, so you're going to get another buffering zone. But now that's going to get depleted, and you're going to see that you're going to get this sharp rise in the pH yet again. You have no buffering capacity, and you have no other groups to deprotonate. We'll see that in the case of something more complicated, where we have a basic R group or we have an acidic R group. Well, in these cases, we're going to get a third buffering region, and we're going to have equivalence points between each of those. In all of these cases, we're going to have a special point called the PI. The PI is going to be the pH at which the amino acid is electrically neutral on net. So basically, in the case of something like glycine, a non-ionizable group, this is going to be where your N-terminus is protonated and your C-terminus is protonated. Another name for when we have something like this is a zwitterion, where we have a full positive charge and a full negative charge, but they balance each other out to give us a neutral molecule. The PI is going to be the pH at which you see this. It's going to be the average of the pKa's on either side of the two most similar pKa values. Here we only have two values, so it's going to be the average of our pK1, our C-terminus, and the average of our pK2, our N-terminus, and this will give us our PI. In the case of something with the basic or acidic R group, it's going to be the one in between the two most similar pKa values. So here and here. So now let's go about drawing one of these. We'll start with an easy example. We'll go back to a non-ionizable one, glycine, and we're going to take this step by step. The first thing we're going to need to do is identify the number of ionizable groups. Remember, there's going to be at least two, potentially three. If we're talking about a non-ionizable side group, we're only going to have two. If we're talking about one with an ionizable side group, then we're going to have three. And if we look at a table of amino acid pKa values, we'll see that we have, we can get a pKa1 value. Sometimes this is the pK1. Sometimes you might see it as pKcooH, various things, but this will be one value. Then you'll have your pK2, your NH3 plus group at your at your N-terminus, and then you might have that side chain pKr. And you'll see that the values are going to be slightly different depending on the amino acid. So you'll need to actually look up the pK1 and pK2 values, not just use the same value. But for this case, we're going to have glycine, and so we can look it up and we can get that the pK2 is going to be 9.6 and the pK1 is going to be 2.34. We said that we have two ionizable groups because we don't have an ionizable group for our side chain. And so what we can do is we can go ahead and we can plot out our x-axis extending to two OH minus equivalents. Sometimes you might see this as like NaOH or KOH. But remember that when you add those are just going to dissociate to give you your hydroxide ion. And so you can think about those as the same. You're going to label each tick mark at 0.5, 1, 1.5, and 2. So remember, at the full equivalence worth, that's where you've deprotonated a full group's worth. And at the half, that's going to be where we correspond to our pKa values. Now what we can do is we can sketch the state of each ionizable group at each increment. And so I'm going to basically use this shorthand notation, where basically I have a straight line representing the backbone, where you have the N-terminus on the left and the C-terminus on the right. And then when applicable, if you have an ionizable side chain, this is going to be sticking up. So this will be our R group. I'm going to use a plus sign to represent a positive charge, a minus sign to represent a minus charge, and a 0 to represent no charge. Note that this is a 0 and not an O, so don't think that this is representing like the C-terminus being deprotonated, and that would make it negative. If it's negative, it's going to have this minus charge. So this is just a 0 showing, because what here we're saying the charge. So remember that if you have a basic group, what we call like a basic group, if you have an NH3 group, this is going to have a positive charge when it's protonated. But for the acidic groups, for the COOH for the COOHs, those are going to be neutral when they're protonated, and the ionized when they're deprotonated. And when they're deprotonated, they're going to have a negative charge. So our N group, our NH3 groups are going to go from positive to neutral, and our COOH groups are going to go from neutral to negatively charged. In the case of our non-ionizable R groups, we're going to look something like this, where we deprotonate our C-terminus, then we deprotonate our N-terminus. And so what we want to do is we're going to sketch out each of these points corresponding to the number of equivalents. So basically what I like to do is I like to plot them above the graph, like right above the number of OH minus equivalents. So remember, you have a full's worth at each full equivalent, and then at the halfway between them, you're going to have half of it deprotonated and half of it deprotonated at the site that we're talking about. And remember that these groups are going to deprotonate in order of their increasing pKa. So with your most acidic group first. So in this case, it's going to be our C-terminus. Now you want to also write the charge at each of these states. So basically just sum up the charges for the different ionizable groups. Note that some of these are going to get like a half charge. This is not saying that you have half a charge. What it's saying is that half of them are going to be protonated and half of them are going to be deprotonated. And so that's going to leave you with a net charge of half or minus half, depending on the other charge states and whether the neutral form is is protonated or deprotonated. So in this case, we end up with charge states something like this. Now what we're going to do is we're going to plot those pKa values. And remember that those are going to correspond to the values at our half equivalents. So at our equivalent 0.5 and then at our 1.5. So when I say like half equivalents, basically I'm just talking about the in-between equivalents, halfway in between equivalents. And remember at these points, this is where the pH is going to equal the pKa. So our amount of conjugate acid is going to equal the amount of conjugate base at the site that we're talking about. So we're always going to be looking at one site at a time. And so we start with our pK1. This is going to be our C-terminus, and we can go ahead and we can plot where the pH is going to intersect where the pKa and the 0.5. And then we go ahead and we do the same thing for our second one, our pK2, our N-terminus. So we do the exact same thing, but this time at 1.5 equivalents, because we have that 1 equivalent to deprotonate the first group, and then half an equivalent to deprotonate that second group. Now what we're going to do is we're going to draw our like flattish line around here representing that buffering zone where we have basically enough of the acid to add to the conjugate acid to neutralize any base and enough of the conjugate base to neutralize any acid. So the pH wouldn't change much if you added. But then what's going to happen is you're going to deplete the acid as you add more and more of your OH minus equivalents. When you deplete all of it, you're going to get to the equivalence point, which is going to correspond to full OH minus equivalents. And so you're going to have these are going to be in between the pKa values. And so you can just add these together, take their average, and you would get, for this, you get a 5.97. You can go ahead and go plot out that where the pH corresponds to 5.97, and the number of OH minus equivalents is 1. And this is going to be the steepest point where you get the steep inflection point. And then you're going to start adding, once you add more OH minus, you're going to start deprotonating that amino group, having a buffering condition again, but this time at a higher pH. You're going to enter your second buffering zone, then you're going to deplete that and end up with your steep rise. So what we can actually do is we can actually connect the points to show this. Drawing, remember the steepest part is going to be through that inflection point, and then you enter another buffering range, and then you just deplete it all. We also need to label our PI. This is our isoelectric point, the pH at which we're electrically neutral. So remember that for glycine, this is going to correspond to the N-terminus being protonated and the C-terminus being deprotonated. And in this case, it's going to correspond to one OH minus equivalent. It's going to be the average of the pKa's on either side of it. Then what we can do is we can just label each of these points, A, B, C, D, E, corresponding to their little sketched version above. So we can do something similar if we have a basic R group or if we have an acidic R group. But here we just have a third pKa we need to consider, a third ionizable group we need to consider. But once again, we're just going to be taking things one group at a time. So it's really not that much harder. We just have to first figure out what order things are going to deprotonate. So look up their pKa values and put them in order. Sketch out those states. Go one pKa at a time, drawing those the pKa's on the graph halfway in between equivalents. Plot out your equivalence point midway between those. Draw your flattish buffering line around your pKa values and the steep inflection points through the equivalence points. Connect all those lines. Identify your PI, which is going to be the pH halfway between the two most similar pKa's. Label that, label all of your points, and you'll get your titration curves for something that has a basic group or something that has an acidic group. You'll get those, in these cases, you're going to get these kind of like two inflection points, and then you're just going to deplete things at the end. You'll also have these 3 buffering zones instead of just the 2 buffering zones that you had for something that was non-ionizable. Hope this helps you understand titration curves and be able to draw them. If you want more examples, more practice, go ahead and check out the longer video that I will link to.